Dr. Vanessa Teague is a cryptographer with long-standing interests in elections and privacy. She divides her time between designing new protocols and explaining why other protocols are not secure. Recently, she worked on cryptographic examinations of voting systems in Switzerland and Australia, elections audits in California, and data re-identification in Australia. Please welcome Vanessa to the stage.
Okay, my talk has the cheerful title of "Who cares about democracy?" which I hope is a rhetorical question. I'm going to talk in some detail about some of the analysis that a large number of other people have done, and you can see this talk is based on joint work with a long list of other colleagues. Some of them are cryptographers who worked on the Swiss Post and CITL proof analysis, some of them are statisticians, and some of them are real computer scientists who do constraint optimization for risk-limiting audits. So here's a rough outline of what I'm going to talk about through the next hour. The story goes like this. There are genuine, nifty cryptographic techniques for providing end-to-end verifiable electronic elections. And I'll talk a little bit more about what that is in a minute. But the idea is that you get real evidence throughout the process of how people intended to vote and whether or not their votes were correctly counted. However, the assumptions about how people behave, whether they're going to check properly and so on, are really too strong for government elections. It's too easy to trick people. So really these systems don't adequately defend against bugs and fraud for serious elections. The New South Wales iVote system falls a long way short of this ideal anyway. But, you know, the worst thing that's going to happen is it gets used for a third of the votes in state elections in New South Wales. But that's not actually the worst thing about Australian election software. The worst thing about Australian election software is the Senate count, which is also closed source code from foreign corporations. Now, in principle, this wouldn't be a problem because it's not actually being used for the casting process. You still vote on a piece of paper, right? And we could conduct a rigorous statistical audit of those paper records to double check what the closed source software from foreign companies was telling us about who our senators were going to be. But we don't. Well, you know, at least there are paper records, so in principle we could check, which is better than what's likely to happen in Victorian local government elections if a bill currently before the Victorian Parliament passes. All right, so that's where we're going. Here's a picture of a kind of ideal, generic, end-to-end verifiable election system. The details are complicated, but the principle is really simple. The idea is that the system should provide evidence that it did the right thing with the data at every stage of the process. And that evidence should be something that you can check using your own software, your own code, stuff that you wrote yourself, and maths that you can freely access and understand. Well, okay, understand is maybe putting it a bit strongly, but at least you can give it a go yourself. On the far left-hand side, we have, I'm imagining voters using a machine, maybe a machine they trust, maybe a machine they don't trust, to make an encryption of their vote. And if they don't necessarily trust that machine and they're not sure whether it entered the vote that they wanted rather than the vote that somebody else who put malware on their device wanted to cast for them instead, they should get some actual evidence, some real numbers that they can use on some other device, any other device they want, to double check for themselves whether or not the encryption they made was what they wanted. So I've written, you know, some indicative kind of maths here, right? I'm checking some kind of mathematical function about the vote that was made on my behalf. So the voter gets some proof in a real rigorous kind of mathematical sense, that the vote that was recorded on their behalf was what they wanted. Then the next stage is a public bulletin board. So think of a fancy website with some extra features to make sure that things can't be deleted or changed after people have checked. And each voter gets the opportunity to check that the ciphertext that they made really did show up on that public bulletin board. Now, if we didn't care about privacy, we'd be done, because we could just decrypt all those votes and that'd be the election outcome. But if we do care about privacy, we don't want to just flat out decrypt the votes that everybody uploaded to the web with their identity attached. So one way of dealing with this situation that I've pictured on this slide is to have a series of servers that shuffle and re-encrypt the votes. So they take in a list of encrypted votes, they rearrange it and make them look different, and then they pass that new list of encrypted votes on to the next mixer. Now, the assumption here, remembering that if you're mixing ordinary paper votes in a big box, you kind of don't know what shuffle you applied. But if you're shuffling electronic records, inevitably you know what electronic permutation you coded, or not coded, but chose. So the way that we deal with this inevitable knowledge is we get several different mixers to do the thing. And the assumption is, as I've deliberately drawn them in different politically suggestive colours, because the assumption is meant to be, as long as they don't all collude and all pool their information about what the rearrangement was, then the link between the incoming votes with people's names on it and the outcoming votes that get decrypted should be broken. So that's all good, except now we have to worry about whether those people actually fiddled the contents at the same time that they were helpfully reshuffling for privacy. So again, there is some fancy crypto for doing that, and you can see down the bottom of my picture, I've written proofs of honest mixing on the bulletin board, proofs of honest decryption also on the bulletin board. So this is a complicated mathematical object that we'll look at in a minute, but the idea, again, is that the proof that they didn't fiddle with the results is made publicly available, and anybody can check using code that they wrote or an implementation that they downloaded and compiled themselves. Anyone can check this evidence that the trustees who were supposed to be shuffling the votes really did shuffle honestly instead of inserting or deleting or changing stuff. And then the final step, so far we've got a well-shuffled list of encrypted votes. Right on the far right side, now we need to decrypt them. Right? And some authority has the secret key, or some collection of authorities have the secret key for decrypting votes in the election. And they have to decrypt them and tell us what they are. Now, again, we need to make sure we're not trusting that authority and running the risk that they lie about what the decryption of the votes was. So again, we use some cryptography to force that authority to make a proof that the decryption that they're telling us really does truthfully reflect the encrypted votes that they got. So that's the picture. And although the mathematical details of each component are quite complicated, I hope the principle is clear. It's sort of a different form of openness from the form of openness that the open source community is used to, but I hope it's something that you can see as a valuable thing. We're not necessarily, it wouldn't be strictly necessary, and in fact it isn't sufficient to see the open source code that the authorities say that they're running. For one thing, they might not even be running the thing that they said they were running. But what is meant to be open and completely in the control of any citizen who feels like it is the opportunity to check, to verify the proofs at every stage and make sure that they're convinced that their vote went in right and that all of the votes were properly dealt with once they arrived. Okay. However, there are some big assumptions about this. Let's talk first of all, I'll go into a little bit more detail about what these mixing and decryption proofs are meant to be. So these are fancy cryptographic objects, but the intention is pretty clear, right? It's meant to be an electronic analogy of this old-fashioned physical idea that scrutineers can stand in the polling place watching somebody shuffle a great big box of ballots and then tip them out on the table in preparation for counting them. So there's really two different things. One is we want to prove that they're shuffled properly without being manipulated, and two, we want to prove that they're decrypted correctly and we're being told the truth about what their decryptions are. So earlier this year, Sarah Jamie Lewis and Olivier Periera and I took a look at the shuffling and decryption proofs in an electronic voting system in Switzerland. So this system was being sold by Swiss Post, and the code was originally developed by a multinational company called Cytel. Now, the system wasn't really end-to-end verifiable. It didn't have all the steps in the picture that I showed a few minutes ago, but it did have shuffling and decryption proofs. So it was supposed to provide, at least to some entities, evidence that the encrypted votes that it received had been properly mixed and correctly decrypted. We found 2 bugs when we looked at the code that became available. The first one was in the proof that each mixnet had shuffled properly, and the second one was in the proof that the decryption was correct. So, you know, there were only 2 things that they were supposed to prove. I'm glad somebody's laughing, right? There were only 2 things that they were supposed to prove. They were both buggy. And buggy in this context means that it's possible to generate a proof that passes verification and makes everything look okay, while actually fiddling the votes. So let's see what that looks like. And I said the principle is simple, but the details are complicated. I just need to have a little survey. Who thinks, yay, maths, I love maths? Who thinks, oh dear, how long is the maths going to last? Oh no, okay, that's pretty good. That's more than I usually get out of my students, to be honest. So we're trying to prove, when we're trying to prove correct decryption, we're trying to prove a very specific mathematical fact, and it's written up here on the slides. We assume that there's a bunch of public information. We've got some parameters for the encryption, a public key, and we've got one ciphertext. I'm calling it C0, C1. It's a pair of numbers in this context. And we want to prove that this is an encryption of 1. If you can prove that something is an encryption of 1, you can prove that it's an encryption of anything. So what that looks like as an equation is, we want to prove that there exists an x such that C1 is C0 to the power of x, and that x matches the secret exponent of the public key. Now this is easy to prove, right? All you have to do is tell everybody x, right? All the other stuff is public, and so anybody could go along. If you were willing to tell everybody x, anybody else could go along and just check that these 2 equations are true. Unfortunately, in this context, x is the secret key for decrypting everybody's votes in the election. So the trick here is that we want to prove this fact is true without revealing x. And that's hard. Fortunately, this is kind of a known thing in cryptography. It's like 40 years old, actually. So the solution is a non-interactive zero-knowledge proof of the equality of discrete logs, and you can go and find a paper from the 80s explaining how to do this. It looks almost like this. You pick some random, the prover, right, the authority is trying to prove that they did the right thing, picks a random value that they don't tell anybody about. They make up some commitment values in step 2 that we don't really need to care very much about. Then they generate for themselves a challenge that they're not supposed to be able to predict or fiddle with. In this case, that H is a cryptographic hash function. So they're supposed to take everything they're trying to prove something about, hash it, and then use the cryptographic hash as the challenge in their next thing. And then the next step, step 4, which is the thing that's supposed to be hard, is they're supposed to effectively answer the challenge that they just made for themselves. And you can see, if you look at the verification equations at the very bottom, which are the things that any citizen is supposed to be able to run and check, I hope you can convince yourself that if the prover was telling the truth, then those 2 equations at the bottom are going to work out fine, because basically the thing on the left is just g to the power of z minus cx, and then b1 is just guaranteed to be, again, whatever it is, c0 to the power of z minus cx again. So, you know, get your pencil out and check it for yourself, but it's true. What's also meant to be true, although it's not so obvious, is you're not meant to be able to have a high probability of producing a successful z if you don't really know x. And so the intuitive intuition is, see how Z is a function of X that slides along a linear scale, right? So if you happen to guess C, you might be able to fiddle things so that you can get a Z that works. But in order to be able to succeed with any reasonable probability, you're really going to have to be able to answer this question about Z in step 4 for whatever value of C happens to come up when you hash all your other stuff. So you're meant to be committed to all of your input data before you have to answer the challenge that you've made for yourself. So that's all fine. And the corrected version works and is an old and established thing. Unfortunately, CITL, instead of just using one of the numerous open source opportunities, well-written opportunities to do this from cryptographers who knew what they were doing, they decided to roll their own. And the reason that this third step is bold is that it actually omits an absolutely crucial step. So I said it's really important that you have to hash everything you're proving something about into this value. They forgot to hash C0, right? So that was the first element of the ciphertext. And if you think about yourself trying to cheat on this proof, once you see that C0 is not hashed, it's actually really obvious how to cheat, right? So make up a value for C1, whatever the real value of the thing is. Make up some random values for B0 and B1. Do the hash, do the thing, and then find Z and C0 by solving these two equations at the bottom. Right? So instead of stepping through it in order like you're supposed to and answering your challenge, you start with the bits that you have to commit to, and then you make the verification equations true after the fact by fiddling with those things that are still free. So it just so happens that my valued colleague, Olivier Periera, had already made this mistake himself in his own verifiable voting system and already written a paper a few years previously about how bad it was and what its implications were and how easy it was to cheat. So it didn't take him very long to do the maths for this one. So the implication is, just to summarise, in that picture that I showed you, the cheating, if a malevolent party controls that mixing and decryption process, they can turn a valid vote from a real citizen into nonsense that doesn't make any meaningful vote. They don't have total freedom over what vote to turn it into because there's actually kind of only 2 degrees of freedom and 2 free things in that set of equations that we saw, but they can make it into some nonsense that doesn't correspond to a real vote and still provide a proof that it seemed to be okay. So it took us a few days to do it. It took us days to compile their code, a couple of days to do the maths, and a couple more days once we got the other thing compiling to kind of code up the exploit and check that it passed their little verification test. Now, informally, it'd be obvious that something had gone wrong because, like I said, the votes are nonsense rather than being a valid vote for something else. So I'm going to end the section on, if you like, idealised end-to-end verifiable elections by just summarising some of the good things and the bad things. So on the one hand, this is a really cool technology, and a genuine end-to-end verifiable system like the Helios voting system is useful in all kinds of things. The International Association of Cryptologic Researchers uses a system a bit like this, with proofs that are not broken, for our board elections, for example. But if we were to think about using something like this for real government elections, there are some serious concerns and limitations. The first thing is that ordinary users really need to do some quite complicated work to verify for themselves that their votes are properly encoded. And really, we don't know how to do this. I think it's dubious that whether we know how to do this for first past the post elections. We definitely don't know how to do this well for preferential voting, complicated votes like we have. And if we don't do it properly, then there's the risk that users can be tricked by malware on their computer or people who are pushing them around to vote in a way that doesn't reflect their intentions. So that's a serious problem, and it's really not a solved problem at all. Most online systems give the user, unfortunately, the capacity to prove how they voted. They don't necessarily reveal the vote, but if you fiddle your client carefully and keep the randomness that you use to make your encrypted blob, you can often prove how you voted. That's a characteristic of Helios, for example. It's not a characteristic of all such systems, and in particular, systems where you go into a polling place and make your vote on a computer in the polling place don't always have that property, but it's certainly a thing to worry about. You've probably noticed that actually understanding the verification, actually understanding how to verify the proofs requires significant expertise, which may or may not be acceptable in a democracy. And the final point, which I think is pretty obvious, is that subtle bugs can totally undermine all of the security properties of the whole system. Right? And again, that's a little bit different from the occasional problems that happen in paper-based systems, because you don't, as a result of one little subtle problem, hand over a capacity for total manipulation of all of the votes to one entity. So in summary, I think there are some reasonable ways of doing electronic voting in a polling place, and anyone who wants to come and talk to me about that through the rest of the day is very welcome. But we just don't know how to do remote electronic voting properly in a way that really safeguards the election against manipulation and software bugs. Okay, so that's the good news. This is the most optimistic part of the talk. What does all that have to do with iVote? Well, really not a lot. Remember our end-to-end, our idealised end-to-end verifiable voting system? Let's think about drawing a picture like that for iVote. So the first step was voters got to make an encrypted vote, and they got to use software under their control to check the maths and make sure their vote had been properly recorded as they requested. Actually, in iVote, voters use some JavaScript from Cytle in their web browser to vote. Same company, by the way. And then if they want to verify, they use a different closed source app from the same company to ask them whether or not their vote was properly recorded. It was closed source at election time. So there's kind of this sort of basic logical problem, right? On the one hand, you're trusting some code from a certain company to record your vote correctly, and if you don't necessarily trust them, then you get to ask them nicely whether they recorded your vote correctly. After the election, some of the code was made available under a reasonable NDA, but at the time of the election, you didn't even know what the app was doing on your behalf. So let's update our picture. In the beginning, voters query some closed source software to ask it whether it recorded their vote correctly or not. So they don't get any proof of honest vote recording at all. At best, they get to query something that they can't really examine for themselves. But at least they must have had a public bulletin board, right? So at least you could check that a vote actually went in there for you. Well, actually, no. They have a secret bulletin board. So there's sort of some list of accepted votes that gets passed around within the Electoral Commission, but ordinary citizens can't check that their vote went in there properly. Now, remember we said we needed a series of independently administered mix servers because we were protecting privacy by assuming that they didn't all collude together to reconstruct the pathway of where one person's vote went in and got decrypted. Actually, iVote has one mix server. So, if you get to read information from the mix server, you can see exactly how every incoming encrypted vote corresponds to the subsequent decrypted vote. So it's not anything approaching even the ideal kind of verifiable election system that I already argued was probably not adequate for running a real election. And if you were listening carefully, you might have noticed that it happens to be provided by exactly the same provider whose code we were already having a good look at in the context of the Swiss e-voting system. It turned out, and I was actually quite surprised by this because they'd never had any kind of proofs of, they'd never had any kind of proofs of anything. But it turned out when the information about the first bug that we found in the proof of shuffle, when that went public, the Electoral Commission put out an announcement saying, well, actually, it affected us as well. Now, the Swiss had made their code available 6 months in advance of the election they were intending to run with it, so that they could get some open examination of its security properties before, 6 months before election time. You know, plenty of time to understand and patch. The New South Wales Electoral Commission was already using it for early voting. So I hope you can see the dates from back there. This is March 13th. Election day and decryption was March 23rd, and early voting in New South Wales starts 2 weeks beforehand. So they're already receiving votes on this system. They put out a press release, which I think Justin Hendry just summarised beautifully here. Yes, we do have that critical cital crypto defect, but don't worry, we're going to use it anyway. It got patched. And they put out this press release which says, look, this is an incredibly difficult bug to exploit. It'd be incredibly hard to get access. Nobody could possibly get access to our voting server during our election. It's so carefully secured. We're really careful about what code we run, and we're going to install a new cital patch any day now. Now, that was the first bug we found. What about that second bug we found that I showed you earlier in the process? Remembering that now we realise that they're running basically the same mixing and decryption code. Did that bug in the decryption proofs that I just showed you, which we found out about a few days, like a week or two after this announcement, did that affect them too? Remember, at the time, the code for this system is not available except under a very restrictive NDA that we didn't sign, so we didn't know. When we found the second bug, this is the 22nd of March, day before election day, they put out this press release saying, the Electoral Commission is confident that the new issue is not relevant to the iVote system. This was highly implausible at the time, right? I could have very well believed that they weren't running any of the cital mixing and decryption stuff that Swiss Post had been running, and I could very well have believed that neither bug was relevant to iVote, but it was highly implausible that the first one was relevant because they were running basically the same code, but the second bug in exactly the same code base was not relevant. But we didn't know because we didn't have any access to the code. In advance of the election, if you wanted to have a look at the code, you had to sign an NDA that promised not to disclose anything about your findings for 5 years, which I did not sign. 4 months after the election, it was made available, so like middle of last year, it was made available on much better terms with a 45-day quiet period. So I signed up and had a look. Now, one theme that I want to bring out through this talk is that laws about election software really matter. Switzerland has very good laws. New South Wales has very bad laws. Have a quick look at this one. So this is basically all of the security requirements for electronic voting. The first one says, not that the system has to protect vote privacy, but that if you find out that it doesn't protect vote privacy, you're not allowed to tell anyone. The second one says, not that the system has to be secure, but that if you tell anybody anything about the source code without asking the Electoral Commissioner first, you can go to jail for 2 years. So there's no law that says anything about transparency and openness. This isn't a small sample of an otherwise long and decent set of legislation mandating transparent and secure electoral processes. This is what substitutes for legislation mandating secure and transparent electoral processes. Guess what? Actually, the decryption proof bug was relevant. Now, this is just a little snippet from the note that I read. If you're a real glutton for punishment, you can follow that little link down there and see. And I'm sorry the notation is slightly different from the thing I showed you a few minutes ago, but remember that the crucial fix was they had to hash C0. So the previous broken version didn't hash C0. The easy, simple fix is all they have to do is hash C0. What did they do? Well, I don't even understand why, but for some weird reason, instead of just doing the obvious, simple, straightforward thing and hashing C0, they made up a random value, S1 here, and they hashed C0 to the power of S1. I don't even understand why. Now, first point, it is clearly not the case that it was not relevant, right? Somebody's patched this, they just haven't done it, they just haven't applied the simple and obvious patch that we recommended. Secondly, I'm kind of staring at this for a while thinking, does that fix the problem? It doesn't seem like it fixes the problem. And actually, it's quite easy to see why it doesn't fix the problem. Now, this is all modular arithmetic mod a prime, but the reason that it doesn't fix the problem is actually quite understandable from ordinary arithmetic. The whole point of hashing it here is it's supposed to commit you to a value of C0, right? You're not supposed to be able to do the thing and then make up your value of C0 after the fact. But committing to C0 to the power of some random value that you also haven't committed to doesn't actually commit you to a value of C0, right? You know, even in ordinary arithmetic, that 2 to the power of 6 is the same as 8 to the power of 2 is the same as 4 to the power of 3. That kind of thing is true. In fact, it's even more true in arithmetic modulo a prime. So you can commit to C0 to the power of S1, do the thing, get to the bottom, and then decide exactly what values of C0 and S1 you want after the fact. So it is relevant, and the way they fixed it doesn't fix it. That went down really well. Obviously, if the code had been openly available at election time, instead of 4 months afterwards, we could have done the 2-minute spot check that it took to see whether or not they'd patched it properly at election time, and then they could have run a non-broken version at the actual state election time. As it was, we didn't find out about it until 4 months afterwards, so they ran the manipulable decryption proof during the election because they'd chosen not to make it openly available to scrutiny by people who knew what they were doing. And it's not a hard fix, right? It's a simple fix. It would have been simple to check that they'd fixed it properly. So what can you do? What can you do? Look for yourself, right? If you're willing to sign a 45-day silence NDA, which is, in my opinion, not too shocking, you can have a look yourself. So I only spent 5 minutes looking at the particular thing that we'd already found. There's heaps and heaps of code there, and you might have all kinds of valuable expertise in all kinds of other areas that I don't know anything about and didn't look at. Have a look. If they're going to use it again, you might as well find bugs and get them fixed, and thus raise the standard very slightly above what it is now. And even better, if you have a look at it, you'll be able to make some informed judgments for your own recommendations to your own parliament or people about whether or not this is a good thing to use. So that's what you can do, number 1. Okay, so who's in New South Wales? Anybody use iVote? Nobody. Okay, but you can still look at it, right? Okay, who's from Victoria? Feeling smug? No, because I'm from Victoria too. In Victoria, at the very end of last year, a bill passed the lower house of our Legislative Assembly saying, for local government elections, right, not for state elections, obviously, that the minister from now on gets to choose the voting system for universal use in all local government elections. And the minister can choose either postal voting, which comes with a, few pages worth of carefully written regulations about security and privacy and proper process and so forth, or attendance voting, which comes with an even older set of strong requirements about good electoral process, dating way back to the 1850s when we introduced the secret ballot for the first time, or anything else he feels like with no restrictions whatsoever. So it's clear what the agenda is here, right? Nobody is seriously proposing that we're going to go and vote with bronze discs or little shards of pottery. It's clearly intended to facilitate large-scale, totally unregulated electronic voting compulsorily for everybody at every local government election in Victoria from now on. And it's coming before the Legislative Assembly in February. So if you're in Victoria, in fact, you've got another 15 minutes stuck here in this lecture theatre. Find out who your members of the Legislative Council are. You should have 5. And email them all and tell them to get rid of this, because this is a disgrace. And once we lose the capacity to do genuine democratic elections in local government in Victoria, we're never going to get it back. We don't know for sure that they're going to use iVote, but it's a fair guess that they're probably going to, given that the Electoral Commissioner recently wrote a long, heartfelt opinion piece about how wonderful it was and how it had proven how secure it was. But even if they use something else, it's also going to be bad, right? There isn't a good solution at this point, for remote voting anyway. So, and even if there was, doing it without any legislative minimal standards of any kind would be utterly irresponsible. So, at an absolute minimum, if they insist upon doing this, they should be writing some standards and minimal things about privacy and verification into the legislation. If they're not even going to do that, I firmly believe the whole thing should be scratched. But don't take my word for it. Log in and have a look at the iVote source code and then write whatever email you want to your MLC. Okay, so that ends the first half of my lecture, which is all about electronic voting. The second half is going to be all about electronic counting of paper records. Now, this in some ways is an easier problem. Actually, in every way, this is an easier problem. Because if we've got a bunch of paper ballots that were filled in by real voters, we've sort of got a basis of evidence, assuming that those paper records have been properly secured and appropriately scrutinised on their way into the ballot box and so forth, which is a big assumption, but at least it's an observable assumption based on Australian scrutineering law. And American scrutineering law, for that matter. If we've got a basis of paper ballots, then an electronic counting system may or may not be trustworthy or secure, but it has the capacity to be double-checked. And this is the thing. In the United States, it's a big thing. Those constituencies that have, or those local governments rather, that have paper records that are electronically counted often do serious statistical audits of those paper records in order to check that the electronic count was okay. Those constituencies that don't have paper records of the votes are another question that is, fortunately, outside the scope of today's talk. But there's a lot of sophisticated technical methods, sophisticated statistics for trying to understand exactly what kind of auditing you should do in order to gain genuine, statistically sound confidence that you got the right answer instead of being tricked by a bug or a piece of malware in the counting software. The best method, in my humble opinion, has been pioneered by a Berkeley professor called Philip Stark, and it's called Risk-Limiting Audits. And the idea of this is you start at the very beginning of the election, you decide for yourself what probability of being tricked you're willing to live with. Because if you're doing random sampling, there's always some probability that you're going to be tricked, right? But at least you should know what it is. And then there's a bunch of clever statistics papers by Philip and his colleagues explaining exactly how to do the audit and compute relevant statistics so that you can guarantee that if you were tricked into accepting a wrong election outcome, you would have discovered that trick with high probability. Or as you run your process, you get suspicious and you can't confirm the election outcome, then you just do a full hand count. So this is fine, this is a thing in America. They do it in Colorado, they do it in California and a bunch of other states, Rhode Island and so forth. However, they have this really weird primitive voting system where all you do is choose one candidate out of a list of multiple candidates. And then the audit is just double checking which candidate got the highest tally, right? Except a small number of weirdo progressive counties do this thing they call instant runoff voting, which in Australia is called voting. And they're starting to get into this weird idea that you could have a first preference and then a second preference and then some other preferences, and you could tally up the votes by elimination. Except, and it's a great system, right? But it breaks the risk-limiting audit statistics that they're so proud of putting in place. So we had a project. This is joint work with Michelle Blom and Andrew Conway and Peter Stuckey and Philip Stark, and a bunch of people at the San Francisco Elections Department. We had a project trying to combine our Australian understanding of how preferential elections work with Philip Stark's work on how to do risk-limiting audits. And we ran this as a pilot in the most recent San Francisco elections in November. So Americans have elections in November even if there's no presidential election, right? The news doesn't tend to come all the way out to Australia, but they're always doing something. In this case, they were voting for a bunch of local races like mayor and district attorney and a bunch of other stuff. And they were voting for district attorney by instant runoff voting. So they had 4 candidates, and it actually turned out to be a really close race because there were 2 very politically different candidates for district attorney. It was quite a hard-fought battle, and the end result was really close. So we decided that we'd try and pilot our risk-limiting audit software on that race. Now, there are some important technical details here. First of all, for reasons that you can come and ask me about if you really care, we only got access to the postal votes, not to the votes that had been cast in the precinct, which turned out to be about 2/3 of the votes. So this is not actually providing any evidence for this particular election that this particular election outcome was right. It's just a pilot to give everybody an idea of how this kind of clever stuff could work. So we're just looking at the postal votes. It just happened in this particular election that the winner, according to the postal votes, was the opposite of the winner if you counted the whole thing, because the people who voted in polling places in San Francisco voted overwhelmingly for the other guy, but never mind. That doesn't really affect the maths. Nor does it really affect the principle of how the thing in its ideal form should work. So again, the key concept here is an idea of completely open, publicly available verification and auditing tools. The actual vote counting system, which is a sort of scanning, take a paper ballot, scan it, digitize it and count it system, is a proprietary system from a company called Dominion, whom I would not trust any more than I trust Cytel. No opportunity to look at that code. But we get to look at its answers, right? So we get, at the beginning of the audit, we have this list that says, the 7th ballot in bag 52 has this list of preferences, and the 8th ballot in bag whatever has this list of preferences. So what we do is we make a random selection from the advertised list of supposedly correct digitizations, and then we go and fetch each one of the paper ballots, and we keep a tally of the discrepancies between what Dominion told us the ballot said and what the paper record actually shows. So we need to do 2 things, or 2 different sets of maths here, which I will not inflict on you because, it's nearly morning tea time. One is a very careful analysis of which parts of the preferential election are important. Because if we're doing a whole lot of eliminations and redistributions, that sometimes one of the early comparisons really matters, right? Sometimes if you flip the elimination order early in the process, that cascades into a completely different winner. But usually it doesn't. Usually you actually don't have to care, and usually you can just count it either way and eliminate all the little people first and pay attention to the end. So the tool that we developed with Michelle Blom and Peter Stuckey does a very careful analysis of this particular election and checks which of those comparisons you really need to care about and ignores the rest. So that's the first thing. And then the second thing is, now that we've done this careful analysis of which comparisons you really have to check carefully and which ones you don't, we can then use some software by Philip Stark to do the careful statistics for eliminating the possibility that the comparison was made wrongly. So you can't go and watch that particular election audit, although the citizens could, I should have said. So the people standing here and pointing are officials, but the people who are a little bit blurry on the left are just a bunch of citizens who felt like showing up. Citizens are allowed to show up, and you can see the process for generating the random sequence of ballots. You can see exactly what ballots are fished out. You can see the Dominion's claim about what that ballot was supposed to be. And you can get the code for doing all of the analysis and statistical testing yourself if you want. So in practice it's quite complicated and it's a bit hard to see and so on, but in principle the auditing process is totally open to anybody who wants to, completely redoing the whole analysis themselves with code that's openly available. You can even think up some cleverer statistical tests or some different statistical tests if you want, or you can check other facts if you want. And again, what you can do is try it yourself. So the first link is for the preferential voting analyzer from Australia, and the second link is for the nifty statistics for actually testing the facts. Okay, so we see this structure, completely different structure from electronic voting, right? But very similar kind of philosophy about how to check it. The thing isn't necessarily very open, but there's a completely open possibility for citizens to check every step of the actual data for this particular election. What does this have to do with the Australian Senate count? You probably have already guessed, not a lot. This is a transcript from the only hearing so far of the Federal Joint Standing Committee on Electoral Matters. Senator Larissa Waters is asking the Australian Electoral Commissioner, Tom Rogers, about the integrity of the Senate count. She starts off by saying, did the AEC attempt to ensure the quality of its data entry by manually checking the preferences recorded in ballots' XML files against the physical ballots or images of them? If so, what proportion were checked? And who did that checking? Right? Not a hard question. Mr. Rogers isn't quite sure. He's going to take that one on notice. He's not sure whether there was any attempt to check preferences out of the closed source software from Fuji Xerox and Cytel against the physical ballots that Australian voters filled in. So Senator Waters continues on undaunted. She says, okay, was there an estimate of the error rate of data entry for the Senate scanning solution? And she's not brave enough to ask what that error estimate was. She just asks whether there was one. The Electoral Commissioner can't remember. He's not sure. Finally, she's a very brave woman. She says, okay, the last time we did this, right, the last time there was a parliamentary inquiry into the previous election, we recommended that an independent, impartial expert scrutineer be appointed for each state and territory. Did you do that? And all of a sudden, Mr. Rogers' memory is right on the ball. He remembers exactly why the very idea of independent, impartial expert scrutiny implies that Senator Waters she just misconceives the role of the AEC. She doesn't really understand what they really need. But before he launches into a long explanation of why it's just a mistake to even think about such independent, impartial scrutiny, which unfortunately didn't fit on, maybe fortunately didn't fit on my slide, he says, well, first of all, it was a recommendation only. It wasn't actually mandated. And then he goes on to say that they didn't do it. Now, I actually think this is a little bit of truth that is really important for the question that I think we need to answer, right? It was a recommendation only, it wasn't mandated, so we didn't do it. And I'm guessing, but one possible guess is that that's actually the true answer for the previous 2 or 3 questions as well. So what can we do? Well, I've now looked at not only election systems, but electoral regulations and legislation in Switzerland, California, New South Wales, Victoria. The Swiss internet voting regulations are really, really good. They're detailed, they're thorough, they're oriented around privacy of individual votes, transparency of the process, publication of the source code, and so forth. They're not perfect, but they're really good. Switzerland found out about their problems as soon as they forced the source code to be open. Right? New South Wales found out about their problems 12 days before election day, when it was just not feasible to patch it properly, and they obviously didn't patch it properly. California has, again, not perfect, but pretty decent laws about election auditing. You have to either conduct, I think it's a 1% manual tally or a rigorous risk-limiting audit, and this is mandated by California law. Australian Senate scrutineering rules just haven't been updated since back in the old days when they counted them on paper, which was a long time ago. And at best, what they say is roughly that the Electoral Commission has to allow scrutineers to stand in the room while they do their thing on their computers, which really doesn't say anything about providing meaningful evidence that what the computers are doing is correct. So it seems to me that in the case of the Senate count, there's a really, really simple solution. We don't have to write the perfect law, we just have to write something that says there must be a meaningful statistical audit of the paper ballots against the public list of digitised preferences that comes out of whatever Fuji Xerox and Cytel software they use to derive it. And that audit, even if the process of deriving it isn't public, and they've fought long and hard to keep the source code of that system secret, as long as the process of auditing is openly available to genuine scrutineering, then we should be able to get some kind of evidence that the Senate outcome they announce is correct. And they're not going to do it without being forced, right? So it has to be mandated in legislation. So here's my little summary of the state of Australian election software. There are reasonable solutions for electronically assisted voting in a polling place, which I haven't really talked about very much, but they exist. There's plenty of sensible things to do. We just shouldn't be doing it over the internet because we don't know how to do it properly. It's just too easy to fiddle the results. And even if the standard of iVote was substantially improved up to something approximating that ideal standard that I outlined at the beginning, we still don't really know how to make sure that ordinary voters can verify that the vote that's going in accurately reflects their intentions. So we should just stop. Or not start, as the case may be. The Senate count is also, I think, a serious risk for undetectable electoral fraud, particularly with those last few seats that get allocated after lots and lots of preference shifting has gone along, because there's no independent count. Like there is for the first few seats, you kind of get an idea based on counts in the polling place of how many first preferences go to the major parties. And I think it would be hard to fiddle that very much. But I think by the time we're talking about the half a dozen seats in any given election that go down to lots and lots and lots of preference passing and are quite hard to predict in advance, that's really a risk that is totally dependent on this completely obscure, foreign designed and implemented software, and we really don't know what's going on. However, we're in a much better position than we are for internet voting because we've got the paper records of how Australians really voted. So all we have to do is a rigorous statistical audit in the presence of scrutineers with meaningful opportunity to actually double check the numbers and make sure that the electronic results accurately reflect the paper ballots. Okay, so in my last 5 minutes, I want to end on a slightly upbeat note, even though it's pretty scary. I've been thinking about a new project, right? I don't necessarily want to spend all of 2020 picking holes in bad software written by other people. So here's one suggestion for a new thing that we could build. Democracy is a lot more than just elections, right? And anybody who, well, I at least got quite engaged in the shocking train wreck that was our anti-encryption laws that passed at the end of the year before last. A whole lot of intelligent people spent a whole lot of time trying to persuade various members of Parliament not to do it, or at the very least to amend it in some way before they did it, which is a process I never want to have anything to do with ever again. But the Parliament is actually quite open about its bills and proposals and legislation, right? You can get the text of just about any bill that's proposed. It's available under Creative Commons. There are already a bunch of really good organisations like the Open Australia people and the Right to Know that put up this legislation. What if we had some kind of nice little cryptographic voting and open source amendment scheme that let people make suggestions for editing legislation, vote up or vote down other people's amendments, maybe make some suggestions for questions in Senate estimates, or just actively participate a little bit more as input into this process, rather than writing 50,000 different submissions to successive inquiries that ignore what we write. I also kind of like the idea of putting up a version that lets teenagers practice debating online, right? If you're not from Melbourne, you may or may not have been subjected to the formal parliamentary kind of debating thing that we make teenage children do. We make them take a political issue and have this sort of back and forwards between different private schools about whatever, euthanasia or abortion or whatever. But we just tell them to stay off Twitter until they're 18, and then they just go on Twitter without any practice. We could use a system like this to give them some practice about participating in democracy in an electronic way, and crypto can do a good job of protecting people's privacy while also aggregating their opinions and proving that they were truthfully aggregated. So I'd like to do something like this, and I'm going to be hanging around for the rest of the day, and anybody is welcome to come and either tell me that this is a bad idea, or tell me that you've got a better idea, or refine this idea or something. The total lack of a secure Australian digital ID makes it hard, right? It's going to be hard to trust any kind of aggregation that is built on not really knowing who we're talking to, but I think we just have to accept that it's not going to be perfect, but maybe it could be okay. All right, I am now done. Questions are welcome if there's time, or questions are welcome throughout the rest of the day. I'll be here.
Thank you very much, Vanessa. We are out of time because morning tea is being served now. But first, a small gift from us to you. Thank you very much for presenting, and thanks for the early morning maths.